One special interference of interest is the standing waves. If you tie a string from one end to the wall and the other end to a vibrating blade, we will have this pattern of waves. Waves will be generated in the string, reflected from the wall, and as they are reflected, there will be a phase change of half lambda, as you can see. And this pattern here is called a standing wave. The interference between the incident wave and the reflected wave creates a standing wave. The molecules in the string will be oscillating up and down with the wave, up and down with the wave, okay, while the sound on the string will be propagating along the string. The points of attachments to the wall and all other stationary points are called nodes. So here we have a node, here we have a node, and in the middle here we have a node. Node simply corresponds to zero displacement. The distance between adjacent nodes is half a wavelength. Half a wavelength. That is the distance between adjacent nodes. All points on the string oscillate together vertically with the same frequency. All points on the string oscillate together upward, downward with the same frequency, but different amplitudes. The amplitude for the oscillation will be the highest here in this region, and here it is zero. And in between, it will be changing as we move along the string. The standing waves on strings can create all kinds of frequencies, all kinds of situations. The first situation, the whole string is equal to half wavelength. This is half wavelength. So L equals 1/2 lambda. This is called the fundamental or first harmonic for the oscillation. Fundamental or first harmonic. So in this situation, lambda is equal to 2L. Lambda is equal to 2L, or L is equal to 1/2 lambda. Okay, so lambda equals 2L. If lambda is equal to 2L, frequency is equal to velocity divided by lambda, so it is velocity divided by 2L. This is the fundamental frequency for the string in this situation. On the other hand, the velocity of sound along the string is defined by the tension force divided by the linear mass density, the density per unit length. So we can substitute this value for the velocity in this equation in order to get this equation for the frequency. The frequency of the first harmonic or the fundamental then is 1/2L square root of F divided by mu. F is the tension force applied to the string, and the mu is the linear mass density, the density per unit length of the string. The second situation, when the standing wave is created like this, in this case, the whole length is equal to 1 lambda, 1 wavelength. This is 1 wavelength here, what we are seeing. So L is equal to lambda for the second harmonic. L is equal to lambda. Therefore, F equals V divided by lambda. And if you compare this to the fundamental frequency, this is twice as much as the fundamental frequency. Then the third harmonic, the length now is 1.5 lambda. This corresponds to a third harmonic. We can calculate the frequency. It's 3 times as much as the fundamental frequency. If you check on the string that is oscillating, you will see nodes here and along the string, and there are anti-nodes. Usually anti-nodes correspond to maximum displacement from the equilibrium position, and node corresponds to zero displacement. So in general, for the nth harmonic, we have Fn. This is equal to n multiplied by the fundamental frequency, F1. So you just multiply n by the equation for the fundamental frequency. That was 1 over 2L square root F over mu. So now we multiply it by n. N is an integer. Which of the following frequencies are higher harmonics of a string with fundamental frequency of 150 Hz? Have these suggestions. To answer this question, we know that higher harmonics need to be integer multiples of the fundamental frequency. Okay, so 200 is not an integer multiple of 150. 300, yes, this is twice 150. 400 is not integer multiple of 150. 500 is not integer multiple of 150. 600, yes, this is 4 times 150. So the answer here would be 300 and 600. These both corresponds to higher harmonics for the 150 Hz source. This is a nice illustration for standing waves on a string. And as you can see, we have the nodes. This is a node, this is a node, and this is a node. And we have the anti-nodes. And for other parts, the amplitude of the oscillation will be changing between 0 for the node and maximum amplitude for the anti-node. This is how sounds are created